You have felt small before, standing on a beach at night, looking up. Now hold this. Out there is an object where 1 teaspoon weighs 1 billion tons. It is the crushed core of a dead star. So dense a sugar cube outweighs every car on Earth. There is not one kind. There are 11. One spins 700 times a second. One would unmake you from 1,000 miles away. In 9 minutes, every kind. Start with what a neutron star actually is. When a star far bigger than the sun runs out of fuel, its core collapses in a fraction of a second, and the outer star explodes as a supernova. What is left behind is the core, crushed beyond anything you can picture. Gravity squeezes it so hard that protons and electrons are jammed together into pure neutrons, packed at the density of an atomic nucleus. Take everything in the sun, its entire mass, and crush it into a ball about 12 miles across. That is a neutron star, a whole star compressed into the size of a city. The surface gravity is so extreme that if you dropped a marshmallow onto it, the impact would release the energy of an atomic bomb. Its crust is a crystal of iron 1 billion times stronger than steel. And under that crust, matter behaves in ways physics still cannot fully describe. This is the foundation. Everything else tonight is a neutron star doing one specific extreme thing. And the first thing it can do is spin and become a lighthouse. A pulsar is a spinning neutron star with a beam. As it collapsed, it inherited 2 things from the original star. Rotation, wound up faster as it shrank, and a magnetic field concentrated into something staggering. That magnetic field funnels radiation out of the 2 magnetic poles in tight beams. And if the star's poles are tilted from its spin axis, those beams sweep around like the light of a lighthouse. Every time a beam crosses the Earth, we see a pulse, steady, precise, like a cosmic clock. The first one was found in 1967 by a graduate student, Jocelyn Bell. She spotted a signal so regular that she and her advisor half-jokingly labeled it LGM, Little Green Men. Then they realized it was a natural object. It was the Crab pulsar and its siblings that revealed the truth. These pulses come from the collapsed hearts of dead stars, 30 times a second or more. Some pulsars are so reliable that they keep time better than atomic clocks on Earth. Astronomers use them as a navigation grid, and any spacecraft far from home could in principle fix its position from their beats alone. But the truly fast ones spin at a speed that should tear them apart. Some pulsars do not spin 30 times a second. They spin hundreds of times a second. The fastest known, a millisecond pulsar buried in a distant star cluster, turns 716 times every second. Try to hold that. Picture a ball the size of a city, more massive than the sun. It spins so fast that its surface moves at 1/5 of the speed of light, and it does not fly apart. Its own gravity is strong enough to hold it together. But here's the strange part. These are old stars. A neutron star should slow down as it ages, not speed up. So how is an ancient one spinning fastest of all? Because it cheated. A millisecond pulsar lives with a companion star, and it has been pulling matter off that companion for millions of years. That stolen matter spun it back up, like water hitting a mill wheel. Astronomers call them recycled pulsars. Dead stars spun back to life by feeding on a neighbor. The spin-up takes hundreds of millions of years, and the result is an object that keeps better time than most atomic clocks on Earth. And one type takes that violence to the surface. A magnetar is a neutron star with the strongest magnetic field in the universe. An ordinary neutron star's field is already 1 trillion times stronger than Earth's. A magnetar's is 1,000 times stronger still, around 1 quadrillion times Earth's magnetic field. Numbers that large stop meaning anything. So here's what it would actually do. If a magnetar were as far from you as the moon, its field would scramble every credit card and wipe every hard drive on the planet. Come within 1,000 miles, and it would pull the iron from your blood. It would distort the atoms in your body. You would stop being chemistry before you felt it. Only about 30 are known out of some 3,000 neutron stars. They are young and they are unstable because a magnetic field that strong strains the crust from the inside until the crust cracks. And when a magnetar's crust cracks, it does something almost nothing else in the universe can do. In 2004, a magnetar called SGR 1806-20 cracked its surface, a starquake. In 1/10 of a second, it released more energy than our sun produces in 100,000 years. The blast crossed 50,000 light years and struck Earth's atmosphere, compressing our planet's magnetic field and disrupting radio signals from a star half the galaxy away. And it barely registered on the star itself, a single crack in a crust. That is a magnetar, powered by a field that can wound a planet from across the galaxy. The next type is quieter because it is busy eating. When a neutron star orbits a living star closely enough, it feeds. Its gravity tears a stream of gas off the companion, and that gas spirals down onto the magnetic poles, slamming in at nearly the speed of light. The impact heats it to millions of degrees, and it blazes in X-rays. A searchlight powered by cannibalism. As the star spins, that hot spot sweeps past us. An X-ray pulsar. These were among the first neutron stars ever detected because the feeding makes them scream across the X-ray sky. But some neutron stars do not hunt alone. Some are bound to another of their own kind. Sometimes two neutron stars end up orbiting each other. Two dead cores, circling in a slow gravitational spiral. For millions of years, they wind inward, and as they do, they stir space itself, sending out ripples called gravitational waves. In 2017, we caught two neutron stars in the final seconds before they merged. We felt it through ripples reaching Earth. It was the first collision detected this way and seen in light at the same time. What it made is the heart of tonight, and we return to it. First, the neutron stars almost no one ever sees. The ones that just sit in the dark and cool. Most neutron stars announce themselves. A beam, a burst, a feeding frenzy. But some do nothing at all. An X-ray dim isolated neutron star has no companion to feed on and no strong pulse to send out. It just sits alone, radiating the leftover heat of its birth, cooling over millions of years. No fireworks, no signal, just a warm ember of a dead star, drifting alone, seen only because it faintly glows in X-rays against the cold. Among the loneliest objects in the galaxy, a whole life reduced to a warmth no one would notice, and a close cousin hides somewhere even harder to reach. Some young neutron stars sit hidden at the exact center of a supernova remnant, the cloud of debris from the explosion that made them. These are central compact objects, newborn neutron stars, still wrapped in the wreckage of their own birth, giving off steady X-rays but no pulse. We are seeing them moments after they form, buried in the shell of the star they used to be. But a few neutron stars flicker in a way that took decades to explain. Some neutron stars do not pulse steadily. They flash. A rotating radio transient sends out a single burst of radio waves. Then it goes silent for minutes or hours before flashing again. They are so erratic it took years to realize these were pulsars. And then there is the most powerful flash of all. A fast radio burst releases, in a single millisecond, as much energy as the sun puts out in days. First seen crossing billions of light years from other galaxies. For years, no one knew what caused them. Then, in 2020, one went off inside our own galaxy, and it came from a magnetar, a cracking magnetar, firing a flash of radio energy across the universe. The most extreme signals in the sky traced to the most extreme stars in the sky, which leaves the strangest possibility of all. Come back to those two neutron stars spiraling together in 2017. When they finally touched, they did not just vanish. In the instant they merged, the collision forged a wave of the heaviest elements in the universe and flung them into space. Gold, platinum, the elements too heavy for an ordinary star to ever make. That merger, and others like it across cosmic time, are where those metals come from. And yet, the gold in a wedding ring was forged in the collision of two dead stars billions of years ago. It scattered across space long before the Earth existed. The most valuable thing a person can wear is the debris of two corpses that fell together. You are surrounded by the aftermath of neutron stars. At the very edge of what physics allows, there may be one more type. Push a neutron star close to the mass, where it would collapse into a black hole, and the neutrons themselves may break down. They dissolve into their raw building blocks, quarks. That is the densest matter that can exist without becoming a black hole, a quark star. We have candidates, but none confirmed yet. If they are real, they are the last stop before matter gives up and vanishes behind an event horizon, the final object standing at the border of nothing. Which brings us back to that beach. 11 kinds of neutron star, a city-sized core with the mass of a sun, a lighthouse spinning 30 times a second, a dead star spun back to life at 700, a magnetar that can wound a planet from across the galaxy, two corpses whose collision made the gold on someone's hand. Everyone is the same thing, the crushed heart of a dead star, enduring what would erase anything else and still holding its shape. That teaspoon that weighs a mountain is proof of how much the universe can crush something and have it survive. The next clear night, when you feel small on that beach, remember, out there are the toughest objects in existence, and they're all just dead stars, refusing to disappear. Subscribe. Next, every type of planet in the universe.